So I'm having trouble.
I'll do my best with that.
And I'll leave it to you, Quentin.
So I've known Zhenguo for about, I think, 4 or 5 years now. One of the hygiene events, first hygiene event I went in Australia. And overall, Zhenguo heads a team of researchers working on hygiene and energy program in UTS, which develops key technologies and prepare workers for the hygiene economy, which is the most important thing is we don't just want to talk about the economy, we want to have skilled people to actually do it. So his research is on boron chemistry for energy conversion and storage, and he has interest in energy storage material, electrolyte, and 2D material. So he had some breakthroughs which have been commercialized, in particular launching a company called Boron Nuclear. Otherwise, he is a very well-awarded researcher. He was awarded a DECRA Fellowship, and that was followed by an ARC Future Fellowship. He's recipient of a number of awards in Japan, in Germany, and at the moment, he is the chair of the International Hygiene Careers Alliance. And he received a University of Hong Kong Vice Chancellor Award for outstanding achievement in research commercialization, impact and engagement, which is very impressive. And after that, the UTS Vice Chancellor Award for Research Excellence in Research Leadership and Development Award. And Zhenguo finally is a graduate of the Austrian Institute of Company Directors, received a PhD from Wollongong, so from here, followed by a postdoc in the US. And finally, I really want to thank Zhenguo for agreeing to give this talk and give us a very nice room for hosting. So thank you very much. I think now I'm going to hand over to Zhenguo for his talk. Let's see, so that should...
I'll stop sharing and yeah.
Wait. Let's see. Microsoft PowerPoint, this one, I think. I see something. HSA. Full screen now. Oh, okay. Can you see it in full screen, Laurie?
No, I can see it, but it's not full screen.
We can see the presenter mode right now.
How do you do that again?
So if on the share screen, click the little arrow that goes upwards, showing you share screen options.
There you go. That's good.
That's not good for them.
Give us a second.
What do you guys want to do?
We can't be biased, so it has to be.
See on both sides.
Looks fine to me.
Yeah, but it's
Not in the room.
not in the room. Let's just
Escape that.
yeah.
Oh, that went black.
No, it just takes our cameras back on.
Okay, that's a start.
Now it's
Too late.
off. And I just want to present this one.
Can you click this one?
Yeah.
Give us a moment.
No.
There it is. It's
Oh,
there.
Almost was.
Let's see this one. Mirror.
Gotta turn off.
I think maybe.
Now you've lost it.
No,
Almost there. Go to full screen on here.
I just want to turn off presentation mode. So we can-
There you go. And when you start the share screen,
Are we good?
yeah, that's good.
Okay. thank
All
you.
right.
So the camera is back on, so I'm going to slowly disappear now.
Okay.
All yours.
Thank you very much. Hello everyone. My name is Zhenguo Huang. I'm a professor at University of Technology Sydney. Before I start my talk, I would like to thank Hydrogen Society of Australia and thank Laurie and Dr. Quentin Meyer and also Van for organizing and coordinating this event. And I also see a few guests from industry, and thank you very much for coming to UTS. Sincerely hope they can find something useful for your job. And also thank all the audience online for coming to my presentation. I actually noticed one thing, that the topic of my presentation today is different from the one I nominated like 2 or 3 months ago. So, but I will give a quick overview on the hydrogen energy research at UTS. But today I'm going to more focus on the hydrogen storage materials. So the hydrogen energy program was launched before COVID. And at this stage, as of now, we have over 100 like academics and PhD students and postdoc combined across 5 faculties. We have experts working on key aspects of the hydrogen program, including like hydrogen production, storage, and data system nexus, techno-economic analysis, safety and social acceptance, and so on. We actually offer a short course during COVID. It was very well attended by actually from people from industry. I think we got more than 10 participants from WUSI back then. Within the hydrogen energy program, we have several key strengths. One of them is hydrogen storage that I'm going to highlight today. And another one is techno-economic analysis. And within this section, we have researchers looking at the key technologies in terms of like production, storage, or consumption. And they are looking at the techno-economic aspect of those technologies, are helping companies to invest and also help the government to support, for certain type of technologies. And UTS also has very good research in the in data science around like artificial intelligence, machine learning. If you look at energy, any type of energy, especially if you talk about like the new the emerging like hydrogen energy, it's tons of data in like production, storage, the value chain, social acceptance, and safety, and so on. So how to collect all the data and how to analyze them and how to optimize all the data in order to have to help the industry to establish their business, or new type of business for them is very, very important. And we have several key researchers who used to work Cyro, leading like multi-million-dollar of research in terms of energy project on board in the team. So that is very, very fruitful for us. In the past several years, we have received this amount of funding from government agencies such as ARC and the CRC, and the industry like domestic and overseas, and also some NGOs. So we are making progress. So here is a quick overview of what we have done, or actually it's more like a few examples. So a few years back, we did this Western Sydney feasibility study on Western Sydney Hydrogen Hub. Western Sydney has been earmarked by state government and also the federal government for major development. We know in a few years we will have the new airport up and running, and there's also industrial zone planned in this area. There's also a $5 billion mixed-use Sydney Science Park. Now, New South Wales state has very ambitious like decarbonization targets. We all know any kind of new energy system, well, actually any kind of energy system is always like infrastructure dependent, right? If we want to have energy supply for those regions with very low carbon footprint, the energy infrastructure we put in place need to be compatible if we're going to use like battery or hydrogen, right? In the coming decade. So this is why we study whether hydrogen can play a role in supplying like green or sustainable fuel for this area. We all know Australia has been a key energy supplier in a way, like supplying like natural gas or coal to neighboring countries, especially like Japan, Korea, Singapore, and China. So we have we've been following their energy policies and also evolving energy policies. And I see audience here like Rock Shi, and they published paper on Chinese energy transition plans. And Australia is a big country, we all know that, but it's also a very small country in terms of population. So there are many regional and remote areas, but those regional and remote areas, they have like a lot of farming activities or mining activities. Those are actually very energy intensive activities. I mean, they're very, very energy intensive. And also those areas are normally very far away from power plants. To get energy into these cities, or I mean, these areas actually can be quite expensive. So we have colleagues working with regional areas and studying like, how to integrate renewable source with the local community, and how to couple renewable resources with the battery or hydrogen storage, and to have like really stable energy supply for stable and also independent energy supply for those areas. So now here I would like to emphasize one thing. While we're talking about the hydrogen, now I started my PhD research actually is around hydrogen storage. This is almost like 20 years ago. And then before that, we have seen quite a few rounds of like interest in hydrogen. But this time, I had a chat with Laurie before the meeting. We think this time the commitment from industry and commitment from government are really unparalleled. This is really because we are going to use a lot more and more low cost renewable energies, from coming from wind or solar, because we have seen in the past like several decades, the cost of electricity coming from wind and solar are going down dramatically, or has been going down dramatically. But they're not available all the time. I guess everybody knows that. So how to store large amount of energy? So we really talk about at the scale of gigawatt hour or terawatt hour over a longer period, not just like 1 hour or 1 day. We talk about weeks or even months. There are many technology, energy storage technology available, right? You have batteries, capacitor. We're using a lot for electronics devices, or even for battery electrical vehicles. But they are really just for small, like for short duration and small scale. If you really want to tap into this renewable energy, wind and solar, like we are actually building a lot of wind farm, solar farm, right? And there are two options for us, like hydrogen or pumped hydro, if we really want to fully tap into this renewable energy resources. Now, pumped hydro is really site specific. Like, we don't have suitable pumped hydro sites all over the place. And so, but hydrogen can be produced in many places and can be stored in large quantities, and they chemically is really stable. They don't really decay, not like batteries, right? You have a self-discharge. So if you think about longer distance, moving large amount of energy over longer distance across vast oceans, and for longer periods of storage, and hydrogen is indeed the best option. During my postdoc, I worked on a few projects funded by Department of Energy, USDOE. Now, back then, the project, that's more than 10 years ago, is really hydrogen for mobilities, for light vehicular applications. And quite often these days, you see publication, people still cite those criteria. They say, the certain hydrogen storage material need to meet certain targets, but actually they are not really relevant. Today's research for hydrogen, around hydrogen storage, is mainly for large scale. It could be for domestic or stationary applications, or could be used for mobile applications. Now, for stationary applications, those criteria set by the USDOE actually is not applicable, because they're very different. So the USDOE right now has a specific term is called hydrogen at scale. So the hydrogen, the hydrogen storage criteria is no longer applicable. So it's really about how we can handle large amount of hydrogen for certain kind of applications, even with very low volumetric density or very low volumetric density. It's not for vehicular applications. If we're going to handle large amount of hydrogen, if we talk about gigawatt, terawatt hour, that translates into like, tons, hundreds of tons of hydrogen. How to handle that amount of hydrogen? It's a really daunting task. If you think about we want to decarbonize blue scope steel in Port Cumberland, I think we need several hundred tons of hydrogen yearly. And you think about we need to have a buffer that we are going to handle tons of hydrogen nearly daily. So it's hydrogen, we all know, is really light gas. It's very flammable. It's not toxic, but very, very flammable. If there's a leak, it can be a huge problem. And if you look at the density here, if you just look at by weight, it has a very high energy density, 3 times of the energy in diesel or gasoline. But by volume, the energy density is terrible. It's only 20% of the energy in diesel or gasoline. But here you see this still is liquefied hydrogen or 700 bar of hydrogen. That means it's highly compressed hydrogen. The reason we want to liquefy hydrogen or compress hydrogen is to improve the volumetric density, right? But when we are using hydrogen, we don't use hydrogen, liquid hydrogen. We don't use hydrogen at minus 253 degrees Celsius. When we use hydrogen, we actually let hydrogen warm up. We still use hydrogen at room temperature. So basically, a lot of energy has been wasted in this process. It's like 30 to 40% for liquefaction. And for hydrogen, 700 bar, most of the commercial hydrogen vehicles these days are using 700 bar of hydrogen, compressed hydrogen. They use carbon fiber reinforced tank because they have to use carbon fiber to reduce the weight, but also for mechanical properties. The high quality carbon fiber is required, which is very, very expensive. Now, so at this stage, hydrogen is predominantly compressed and then stored and then delivered. And for this tubular, quite often it's only like 100, 200, or 300 bar. The tubular itself could be several tons, and it's only suitable to transfer or deliver like a few hundred kilograms of hydrogen. So which is a very, very inefficient process. And for road tanker, this guy will easily cost around 2 to 3 million euros, like certainly over 3 million Australian dollars. And you have to maintain minus 253 degrees Celsius, very low temperature. A lot of energy required to run this one, and for longer distance, it's not really economical. And for liquid hydrogen, and it's mainly used by space agencies. I mean, space agencies normally is funded by government, right? And it's not for like civil application. They can absorb the cost. So to move large amount of hydrogen around, or even to handle large amount of hydrogen for stationary applications, to handle H2 molecules has been really challenging. So this is what I'm trying to say. Okay, so instead of handling H2 molecules or hydrogen molecules, we can introduce a material, a host material that can form some kind of interaction with H2 molecules, either through chemical bonding or physiosorptions. And then you get this hydrogen-rich system. Then by changing the reaction conditions, for example, you warm up a little bit, or you swing the temperature, reduce temperature, or you introduce catalyst, the hydrogen can be released. So in this system, for this system in general, we call it material-based hydrogen storage, right? And mostly it's chemical-based. There are, you probably have heard like a metal hydride-based or chemical hydride-based or physiosorption-based. Physiosorption-based normally work at about like 77 K, like a liquid nitrogen temperature. Again, you can think, liquid nitrogen, that means energy cost. And normally the weight capacity is not that high. We have seen some report on MOF-based like metal or really highly porous material. They can be used to absorb hydrogen, but there's a lot of challenges in terms of recyclability and also the cost, apparently because MOF is still at a very early stage of research. In order to use those kind of system in large scale, there are many factors you have to think about. So first of all, cost, right? If it's really costly, it will never be used in large scale. Probably can be used for niche markets, right? And the capacity for this system, if the capacity is very, very low, you probably can only use for stationary applications. For example, if it's like 1.5%, that is like typical lanthanum nickel 5 alloy, you don't want to move this metal alloy over large distance because it's only 1.5% of the mass is hydrogen. You have to move along to that mass while you're moving around hydrogen, right? If the hydrogen storage, if the system has a higher hydrogen capacity, for example, liquid organic hydrogen carrier, like 6 weights per 10, or some of the system that we're working on in the lab right now, 10 weight %, then you can move the whole system around because you're going to move less dead mass or less inactive mass around. So the capacity really determines the application scenario. The working temperature. Now this is quite important because for certain applications, you need to have temperature to drive hydrogen. Imagine this is like sponge, right? You pick up hydrogen and then release hydrogen. If this process has to be driven by a high temperature, that means you have lower net energy output because high temperature is required. High temperature always means higher energy. So ideally, you want to have the system reversibly working at mild temperatures, right? At mild especially. Kinetics depends on the applications. If it's an onboard application for vehicles, when you accelerate, you want hydrogen to come out as soon as possible. Then you need to have high kinetics. But if it's for stationary application, for example, if I'm going to use this for steelworks, probably you do not need to have like, really fast, high kinetics of hydrogen evolution. And cycling, as I mentioned, if this sponge tend to collapse after 50 cycles or 100 cycles, then it's not good, right? And then we want this system to be ideally to be able to be like a cycle like over 1,000 of cycles. So at this stage, something like a metal hydride that like a lanthanum nickel 5 can be cycled in over 1,000 times, no problem. Not a lot of degradation, but you have to make sure the hydrogen source you are using is really, really pure, because if you have oxygen or water existing in this metal hydride, you are going to form hydroxide, metal hydroxide or metal oxide, and it just become dead. They're no longer active in terms of absorbing hydrogen. And whether we have the infrastructure available. Now, when we talk about battery electric vehicles these days, I don't want to buy one these days because I don't have lots of charging station around me. That's the infrastructure, right? And for the oil, for the gas, station these days or petrol stations, it has take a long time to build up, right? If you have the infrastructure to move the hydrogen storage materials over a longer distance in a safe way, and apparently we will see a quick and wide market penetration. Have I been in the mute all the time? Oh, okay. Can you hear me?
Yep, we can hear you online again. Thank you.
I didn't hear that. Okay. Okay. Yeah. Okay. Sorry for the. Okay. So we talk about if you go to a hydrogen conference, especially like related to industrial application, people will talk a lot about like ammonia or LOC, like liquid organic hydrogen carriers. It's mainly because we have a lot of infrastructure around to handle those kind of hydrogen carriers in large quantities. Okay, now this one is no longer working. Okay, then how to do this? Okay, hey. Okay, okay, this one's great. Another one we have to think about is environmental impact and also safety. Ammonia is really toxic, and also very, very corrosive. But it has really high hydrogen capacity, right? It's NH3. We have been using ammonia for a long time. We know how to handle it, but we have to handle it really carefully. We can't really use ammonia in the metropolitan area, because if there's a spill, ammonia will stick to many different kind of surfaces, right? And if you are going to inhale ammonia in large quantity, you will have irreversible damage to our respiratory system. But ammonia has to be, I mean, can be used for as a hydrogen carrier, but it has to be from isolated point A in terms of manufacturing to isolated point B as a terminal, right? We can't really handle ammonia in like large, in crowded, area. So this has to be, everything here needs to be balanced. It's really, really challenging task. This is why we haven't got any compound or system right now with really wide, acceptance in terms of application. Metal hydride has been used for a long, long time, and I think the very first and very successful one actually is in the during the space competition in 1950s, 60s. They actually used the metal hydride to store hydrogen on board to power the hydrogen fuel cell. Now it's really successful, but we have not seen metal hydride, all over the place, because I mentioned the capacity is quite low, right? So a lot of things need to be balanced, and also the cost actually is pretty low as well. Now, today's talk, I'm going to give overview of some of the systems we're working on in the lab, but not all of them. So if we want to have a higher capacity, right? If you look at the periodical tables, our options are quite limited, right? To have a higher capacity, you can only choose the light elements: boron, carbon, nitrogen, oxygen, right? And then you have a combination of all of these, or some of these, right? So if you have a good combination of all of these, in theory, you can have a higher hydrogen capacity. And some of them, like the OH-based, like it is alcohol-based system, we have a lot of manufacturing, like sites available or plant available globally. We have infrastructure available for storage and shipping, like NH, as I mentioned, like ammonia. And we do have a really vast database or good database on the physical, chemical safety of all of this. We know the compound really well in a way, okay? And we know the environmental impact. We know the risks involved if we're going to use them for different kind of applications. So this is a good start, right? It's a really good start. It has good higher capacity, and all the facility available to handle them in large quantities. And here is a breakdown of some of the system. I just want to give a quick overview. So this is hydrocarbon. Now, hydrocarbon, the two of them are standing out. One is this toluene and methyl cyclohexane, this system. So if you put hydrogen, the chemical term is a hydrogenate toluene, basically react hydrogen with toluene. You see this unsaturated at about 100 or between 100 to 200 degrees, depends on the catalyst. You can convert this one into methyl cyclohexane, and then you heat it up to 200 or 400 degrees, and using typically using like platinum-based catalyst. Normally it's normal metal-based catalyst. You can take the hydrogen out. It's the same as this one. So this one right now, it's being commercialized to some extent by Chiyoda. That's a Japanese chemical company. I think they have run one demo. They shipped different certain amount of methyl cyclohexane. I think it's from bromide to Japan. And this one I think is being commercialized by Hydronius, a company in Germany. But look at all of them. There's a common feature here, right? It's mainly aromatic-based compound. So the hydrogen storage or absorption or desorption is based on, fundamentally, it's based on the formation of CH bond and the cleavage of CH bond. Right, this is why we put this here. It's a CH-based system. Now, for those kind of system, for a long, long time, this is like a century, right? Probably over a century, we know the best catalyst is typically noble metal-based catalyst, and also the temperature is typically about 100 degrees, right? And then the energy cost is high, and the kinetics actually can be pretty slow. And so that's the challenge of that system. Here is a table summarize the physical and the thermodynamic property of those systems, but I'm not going to go through this one. Now, the OH-based system. For the OH-based system, you can think of like alcohol, methanol, ethanol, and also formic acid. So it has O, it has H. Now, you can get hydrogen out from the system, depends on the pathway or method you're going to use. You can potentially generate CO2. Now, this is not something that we really want, because we are working on the hydrogen, right? We want to minimize the formation of CO2. Probably we have to find a way to, well, if we does generate CO2, we can still capture and reutilize if we have a good method, or we can convert it into some other liquid compound, right? But in this way, the capacity drops, like, from this one to this one, half of the capacity. And methanol has its own advantage. It's really cheap, widely available. We know how to handle it. We know how to produce it in large quantities. But there are a few methods to get hydrogen out from methanol. It's still, the decent amount of, quite a lot of research already. Actually, there are lots of demos around the world, but certainly still a lot of problems associated with those kind of system in terms of it will generate CO as well, and then you have to suppress and you have to separate, purify the gas stream. For if you're going to use it for hydrogen fuel cell, right? It's not going to be good for the fuel cell produced by Quentin, right? Because it's going to kill the catalyst very soon. And yeah, here's another form that summarizes all this, the OH-based system. We're working on some of this in the lab, but I'm not going to talk to you. But if we're going to have a chance to visit the lab, I can show you some of this. So another one, NH system. I think I have talked quite a few times about ammonia. Now, the NH system, the one that stands out is ammonia, right? We can isolate nitrogen from the air and we produce hydrogen, whether it's gray hydrogen, green hydrogen, at high pressure, 200 bar, and high temperature, using catalysts, we can produce ammonia in large quantity based on Haber-Bosch process. Very, very energy intensive process, around 1 to 2% of the world energy production. Energy produced is being used actually to produce ammonia. And ammonia has really good infrastructure. We know how to handle them in a large, it can be easily liquefied, and moving, storage, and delivery is very easy. The ideal case is to use ammonia straight away, not split ammonia back into nitrogen and hydrogen gas. Because if we want to crack, this is called crack, if we want to crack ammonia into N2 and hydrogen, that will require a lot of energy, like 7% of energy to 10% of energy in hydrogen itself. Because we need to have like around 500 degrees or 600 degrees, and we need to have a separation gas purification system, because ammonia itself is poisonous to the catalyst in the fuel cell. And there are also some other systems contain NH bond, and the hydrogen storage again is based on the formation and the cleavage of the NH bond. Depends on the system. Like if it's a straight, like hydrogen decomposition, very straightforward, and you can combine this one with some alcohol or diol, and then it follows different kind of decomposition pathway. But we have not. But there are research activities on those compound, but not a lot, because they are very, very expensive, and some of them are actually very, very quite toxic. Okay. Now, instead of cracking ammonia thermally at a high temperature like 500 degrees or 600 degrees, we are thinking about whether we can convert. I'm not talking about cracking this using cracking. Whether we can convert ammonia and into something at the same time generate hydrogen under mild conditions. So in this case, we're actually generating hydrogen by oxidizing ammonia aqueous solution at room temperature electrochemically. So in this process, we don't need to have high temperature, right? We just do it at room temperature. And in this system, we are converting ammonia into value-added nitrite or nitrate. This can be controlled by the catalyst and also by the voltages and different parameters. And at the anode side, we can produce high purity of hydrogen gas. And this can be done. Let me see whether this. So you can see this is H cell. From this side, it's generating hydrogen. It's murky here. There's lots of hydrogen gas bubble. From this side, we generate nitrite or nitrate, depending on the catalyst used. This is small fuel cell. The hydrogen gas goes through this fuel cell, produce electricity, and we just show you the demo. This is something happens at room temperature. Okay, so in our lab, we are mainly working on the hydrogen storage materials. We're not really working on ammonia synthesis, but we're working on how to get hydrogen out from the system. So this is something about the NH system. Okay. Now, BH system is almost done. So just bear with me, okay? Again, light elements, very light elements. If you look at most of the material here, this guy has a lower capacity, but this one has a little bit lower, but most of them have very high hydrogen capacity. Lithium borohydride has nearly 20% of hydrogen, much higher than 10 times higher than a lot of metal hydride, okay? You actually can build like reversible system, but requires high temperature. And you can get hydrogen out from the system reversibly, as I mentioned, depends on the catalyst you are using, typically like a nickel-based. It can enable like 50 to 100 cycles, but typically require like 300, 400 degree. As I mentioned, temperature is a key factor that affect the overall energy efficiency. Higher temperature always means lower net energy output. We've been working on this system for quite some time. It is challenging, but I guess it can be really, really promising for certain applications. So among all those borohydride, I would like to highlight sodium borohydride because it stands out as a really good system for hydrogen storage through hydrolysis. Now, hydrolysis take place at room temperature. It's hydrolysis, right? You basically this compound will react with water forming hydrogen. That's it. So no energy input during this reaction is controllable. And we can use catalysts to control the hydrogen evolution. Now, nearly all the other borohydrides are synthesized use sodium borohydride as a precursor. So this is a great grandfather in all the systems. So for a long time, sodium borohydride has been synthesized using Boron-Schlesinger process. So what it involves is illustrated here. You can see the first step, you need to produce hydrogen using this steam reforming. Okay, at the same time, you generate CO2, but this is gray hydrogen. But you can think about are you going to use green hydrogen instead of gray hydrogen, right? And then you need to produce elemental sodium to produce sodium hydroxide. Sodium hydride. Very, very flammable stuff, right? Paraffin. And then converting borax into boric acid, and then produce trimethyl borate. React these two, you can get sodium borohydride. Very well established process, and this is the predominant process used right now commercially for sodium borohydride production. It's very energy intensive and high carbon footprint. Very difficult to handle, actually. Think about handling large amount of sodium. Okay, now as I mentioned, you can get hydrogen out simply by dumping sodium borohydride into water at room temperature. Why we haven't seen this system commercialized in large quantity? It's because it's very hard to convert this one back into sodium borohydride. As I mentioned, you need to have, if you want to see a system with good application, you need to have, well, reversibility, right? It has to be regenerated in a way, or recharged in a way, or reformed in a way, safely, economically. So we don't have a good method to convert this guy back into sodium borohydride. Now, working with our collaborator, what we have found is, okay, so if we bubble CO2, we got tons of CO2 into this hydrolytic product, we can get this system. Now this system, we can ball mill this one with magnesium. We can get high purity of sodium borohydride, and together we can get CH4. That's the methane gas. So we actually can regenerate sodium borohydride in one pot without using hydrogen gas, without using sodium. And we can also simultaneously, we can convert CO2 into CH4. Now there is a challenge here because we're using magnesium. So magnesium typically can be produced through, again, electrolysis. We hope that there will be improvement in the electrolysis, like in terms of efficiency. The key challenge is here how to get really cheap magnesium. But other than that, this system is beautiful. If you compare this one with the conventional brown cylinder process. So we're working with Boron Molecular and another Graphinex funded by CRCP. We're trying to build up a pilot scale manufacturing of sodium borohydride. Now, as I mentioned, the hydrogen evolution of storage in the system is based on the bond, whether it's a CH bond, BH bond, OH bond. But whether we can construct a hybrid system means the hydrogen production or evolution is driven by a combined like BH bond and NH bond, right? So think about this system. This is cyclohexane. The hydrogen evolution is depends on, it relies on the CH bond formation and cleavage. But in this system, this is isoelectronic, has a similar, not similar, it's exactly same number of electrons as this one. But the hydrogen evolution is driven by this BH bond interacting with this NH bond. So the hydrogen attached to the boron is negative. The hydrogen attached to nitrogen is positive. And you have a strong dihydrogen bond interaction. So it will give off hydrogen at very mild temperature. Okay, so you think about this one, you need to get to 350 degrees to get hydrogen out from cyclohexane. But for this one, only 150 degrees, right? Reduce the temperature means higher net energy output. So I'm going to give you two examples here. Now, one of them is ethylene-diamine, readily available. If we mix ethylene-diamine with ethylene-diamine bisporine at room temperature, we put some commercially available catalysts. We just actually bought this one from Sigma. At room temperature, we can get really high purity of hydrogen out from the system. And more importantly, the system can be regenerated at room temperature. So this project actually is funded by KOGAS, Korea Gas Corporation, world's largest LNG importer. They want to import a lot of hydrogen from China, from Australia. And the reason that we can regenerate this one at room temperature is mainly, we postulate, okay, so we don't have really 100% evidence right now. It's because the formation of this BCN heterocycles. In these heterocycles, it's not really stable. So we can easily break up the cycle and reform the starting materials. Now, another example, as I mentioned, the cyclohexane, we can build an analog with the exact same number of electrons. It's called isoelectronic analog. So for example, like this one, these two have been produced or reported quite a few years back. If you look at this one, the hydrogen evolution is driven by the interaction between NH and BH. You can see from the system this is the end product. We know we don't have BH or NH anymore because the bond is broken, right? It releases hydrogen gas, 6 equivalent from 3 equivalent of the starting material. Now to maximize, to improve the hydrogen capacity, we can put more NH2 or BH2 in the system. And more important, put them together, because next to each other means stronger interaction between the BH and NH bond. This is how we design the molecules, and this is how we make the molecule. And Yandai actually, he made this molecule a few years ago. It does give off hydrogen at fairly low temperature. It started around 100 degrees. It's almost 98%. Very interesting, beautiful molecules. Has this chair structure exactly same as cyclohexane based on the single crystal data. But unfortunately, if you heat up to a very high temperature, it's going to collapse, which is reasonable because it's kind of like organic compound, right? If you heat it up too high, then it's going to collapse. And it's very hard to regenerate the system, but it can be regenerated, but not that good. The energy cost is pretty high. All right, I think that's today I have talked about CH, BH, NH, and OH based hydrogen carriers. And in the lab, we are also working on magnesium hydride, but not a lot, simply because it's very difficult to handle. It's really, really flammable stuff. We have some other, like, system in the lab, for example, like we are making this heterocyclic BCN systems and ammonia decomposition and formic acid production and decomposition and so on. And if you have any interest, we can have a quick look at the lab. But this is all from me. This is a quick overview of the system. Lastly, I would like to thank all my student postdocs who have contributed to the work, and also the funding agencies for brief enough listening my proposals and for their support. And lastly, thank you guys very much for coming to UTS, and thank everybody online. Hopefully you can I only use the laser pointer upon the screen, but not on the the Zoom like slides. I'm sorry for that. I guess we can have some time for Q&A. Oh, already? Okay.